Hello everybody, how are you people? I am back again with a very new episode of our crash course, and today's topic is mechanical properties of liquids part 2. So first let's just tell me, am I audible and visible to all of you? And just tell me how many of you are present over here. Chat में बताइए, hi लिखिए everyone. Am I audible? Am I visible? So that we can start the session. The session is going to be a very nice one. In the previous session, I suppose आप सभी ने देखा होगा, we had discussed so many things about fluid mechanics and also about solids, how stress strain are changing and how things are different, and what all things occur whenever I talk about stress strain and so many things. So now in this lecture what we'll be starting is we'll be dealing with all the concepts of fluid mechanics, that is when fluids are not at rest but fluids are in motion. Starting में we'll have few concepts and topics about buoyancy, Archimedes principle, जो कि हमें पिछले लेक्चर में कंप्लीट करने थे, बट वील बी डूइंग इट नाउ. एंड उसके बाद फटाफट वील जस्ट जंप टूवर्ड्स फ्लूइड्स इन मोशन एंड जितने भी कॉन्सेप्ट्स हैं बर्नौली थ्योरम से लेके व्हाट ऑल एप्लीकेशंस आर देयर ऑफ बर्नौली थ्योरम. देन आफ्टर दैट उसके बाद हम आगे बढ़ेंगे तो सरफेस टेंशन, then viscosity क्या होती है, then capillary rise क्या होता है. So we'll be discussing about all those things. Okay, so let me give you a brief about myself. My name is Adarsh Rai and I'm a graduate from NIT Bhopal. I have a very rich experience of around 6 years and I have been teaching students to clear competitive exams like JEE Main, Advanced, even NEET as well. And if I talk about Extramarks, so Extramarks has a very good record in this JEE NEET segment. We have made sure that out of every 7 students, one has cleared JEE Main, and this result is going to improve in the coming years very nicely. And if I talk about the content, and I'll be telling you which content I'm talking about. So the content in the app, so you can find the link to the app in the description. You can download it right away, and all the questions which you'll see over there, all the tests which you'll give or solve over there are curated by experts who are from the NIT, who are actually from NIT and IIT. Okay, matlab they already have cleared this exam and they know very well what are the tips, what are the tricks, and how, what tempo should a person have such that he should be able enough to clear this exam. Okay, and आजकल के जो questions आ रहे हैं ना, जिस topic से ज़्यादा आ रहे हैं, देखो suppose मैं अगर mechanical properties of liquids की ही बात करूँ, so हर साल near about 2 to 3 questions you can encounter of mechanical properties of liquids, and more than that इसके जो concepts रहते हैं, based on its concepts the questions can be infused in some other topic as well. So जिस टाइप से, जिस पोर्शन से, जिस सब टॉपिक से ज़्यादा अमाउंट ऑफ क्वेश्चंस आ रहे हैं इन द रिसेंट ईयर्स, those are the questions which have been created, and even इस crash course के content में भी you can just get a glimpse of that. So we have picked those concepts only and we'll be stressing on those which are actually the hot topics in the recent years, and the questions based on them have been asked by NTA in the coming years, in the previous years as well. Now let's move ahead. As I told you, you can find the link to our app in the description, and there you can practice unlimited amount of questions. There is no bar that this many amount of questions you can find. You can even find the solutions to the questions as well. If you have any doubt, you can find video solutions as well. You can find written solutions as well. More than that, you can also avail the benefit of giving tests and just know where you are standing. You will get those ranks, and trust me, this platform is used by millions, so you will get a clear picture where you are actually standing, because at the end you obviously have to fight over there with all the audience from India, all the aspirants who are giving JEE Main. So to give this test, you will get a very good result. Apart from the result, you will also get an analysis in which questions you did, you took more time than usual, or what are the questions or what all topics you are not very good at. And after the analysis report, you can further practice questions from that topic. Even you can hear to our lectures as well, which are freely available to you at 5 p.m. every day. So this is a win-win situation, guys. You should definitely join it. And now let's start our discussion with the first topic of buoyancy. Okay, so how many of you are there? Hi Royal, hi Komalpreet. Okay, Sachin, good evening, and Shruti, good evening. Okay, now let's start our discussion, and the first topic which we are going to start is buoyancy. So what is buoyancy? A very general concept, and trust me, it is actually surrounding you everywhere, whether you go and take a bath. So in that, if you can ever feel that your plastic mug is not drowning in a bucket full of water, or suppose in place of that you place a steel ball, then it drowns, and on the contrary, if you place in that same bucket a plastic ball, it floats. So what is the reason behind all these things, and how those heavy ships made of so many thousands and thousands of kgs can easily float on seas and oceans, and just a tiny piece of stone, when I just throw it in water, it sinks to the bottom. And why are these things, why are these phenomena happening? The reason to them is only buoyancy. So what buoyancy is actually, that the reason for a buoyant force is the pressure exerted by fluids. Okay, so and another thing also in it is that pressure increases as we go down and down. So what I actually mean to say is that suppose I actually have a bucket full of water, okay, and any liquid has been placed over here. So suppose water has been placed, and its density is obviously 10 to the power 3 kg per meter cube. And suppose I place a block, a normal cubical block. It's a very standard case just to understand how buoyancy actually affects all the bodies. So what happens is, as the molecules of this liquid are continuously in motion, they are moving rapidly in random direction, every possible direction, and so they'll be hitting the surfaces of this cube, as obvious, since they are moving randomly in any possible direction, they'll be definitely hitting the surfaces of this cube. And because of the collision on the surface of this cube will definitely experience a force because of the continuous collision of the water molecules on it. Okay, so that force will obviously be perpendicular in direction. Okay, so it will be perpendicular to its sides. So you are just able to see a square shape, but it's a cube, right? So it will have 6 faces. So there will be an upward face as well, and there will be a downward face as well. So this force is obviously on the upward face, and there's a downward face. There will be 2 forces from front and back as well. Okay. Now what happens is, we very well know that pressure in a fluid increases as we go deeper and deeper. So the pressure exerted by the fluid over here will obviously be more than the pressure exerted by the fluid over here, definitely. And if I talk about these 2 sides, the lateral sides, the left, right one and the front and the back one, there the pressure is almost same. Why? Because it's at the same horizontal level. So the pressure exerted over here and the force experienced by the walls over here will be equivalent to the force experienced by the walls over here. They'll be just cancelling them each other. So the forces experienced on the lateral surfaces of the entire cube will amount to 0, but there will be a difference in the force exerted by the top and the bottom face, and this is the reason why buoyant force comes into picture. So what happens is, since the pressure over here at the top surface is lesser, so the force exerted by the molecules on the wall of this cube will be lesser as compared to the force experienced by this cube from its bottom surface, and this is the result. This force is more as compared to this force, so overall this cube experiences a net upward force. Okay, it obviously experiences a net upward force, and this force will never come into action if the body has no height. Okay, suppose the body is a 2-dimensional figure and just placed like this. So then in that case, no buoyant force will obviously come into action. But are you serious? Can you create a body which doesn't has any depth? You can try your best, but obviously it will have some depth, and based on that depth only it will experience a buoyant force. Okay. So this force, this buoyant force, is actually of great amount whenever I talk about liquids whose density is in the range 10 to the power 3 kg per meter cube. Now if I talk about fluid, or if I talk about air for being specific, so air is everywhere, right? Air is everywhere. So its density is near about 1 kg per meter cube, and even lesser than that. So this buoyant force also comes into play while we are in air, where we keep an object like this in air, but not in that great amount, because that density is obviously very less. Okay, and even if you want to observe the effect of buoyant force in air, then you must have seen those balloons filled with helium gas, right? So those helium gas balloons, they actually float upward, they move upward, and the reason to that is only buoyant force. So buoyant force comes into picture because of the density of the fluid, the depth and the pressure exerted by the molecules of any fluid. They are continuously moving, right? So because of their movement, they exert a force, and this force is obviously what buoyant force is all about. But we have written it, we have understood it at the name of buoyant force, but it was actually detected back in 1600s, and I don't remember the date, but it was detected by Archimedes, and he gave its principle, and this principle is actually what buoyant force is all about. So buoyancy is all related with Archimedes principle. So what his statement actually is that I'll just give you a very clear picture. So it states that when a solid body is immersed wholly or partially in a liquid, then there is some apparent loss in its weight. This loss in weight is equal to weight of the liquid displaced by the fluid. This is a definition part, a bit tricky to students to remember it or to understand it. I'll just give you a very good example. So what happens is, suppose you have a glass tumbler and you have filled it completely with water. You have filled it completely with water. Take this side a bit higher, and this side you have completely filled it with water. So any amount of water, if you fill in it, it will get spilled out. Okay. So here you have one more container which is empty. Now what happens is, suppose you have an object. Okay, you have an object of any random shape. This is the shape of the object. Okay, and this object you are actually placing inside it. So what happens, as you begin to move this object inside this fluid, some amount of water will definitely fall out of this tumbler into this section, into this container, and depending upon what amount of object you have actually inserted in this bucket, the amount will be displaced, the water will be displaced over here. And what will be the relation? Basically the relation will be that the volume of this object which is submerged in water will be equal to the volume of the water you have got collected over here. Okay, the volume will be same, not the mass. So it happens many times that students confuse it with mass, that the mass over here will be equal to the mass over here. No, that's not the case. The volume of the submerged, whatever amount of object you have submerged in it, say suppose I am in a position, I have submerged this much amount. So the volume, this volume will be equal to this volume of water which has been collected over here. And if I am able to submerge this entire object inside it, now suppose if I am able to submerge this entire object inside it, so the volume will be somewhat like this over here. Okay, so this will be the volume collected for this entire object. Now whatever is the weight of this displaced liquid will be the amount of buoyant force acting over here. Are you clear with it? What Archimedes principle says is, and it is completely in sync with what buoyant force is also all about. Okay, so buoyant force can be derived or can be understood using Archimedes principle also. So the weight of this fluid, whatever is the weight of this fluid, just remember the weight of this fluid will be the amount of buoyant force being exerted on this object. Okay, so what will be the weight of this fluid? Do you know? Yes, we very well know. So weight can be calculated. We can write the expression to be that the buoyant force exerted will be equal to weight of the displaced fluid. That's what Archimedes principle is all about. Let's calculate the displaced fluid weight. So I can write this weight to be mass of water into G, obviously that's weight, and mass of water can be replaced by density of water into volume of water, right? So I can write it to be density of water, okay, into volume of water, whatever volume you have collected over here, into G. Perfectly clear? Any doubt you can just ask me up. So it's volume into density of water into G. Perfect. Now this will be equal to buoyant force being exerted on this body which is partially, or I say completely immersed in it. Okay, so this body is completely immersed in liquid and it is experiencing a force equivalent to FB, and this force is obviously equal to displaced fluid's weight, which is given by Archimedes principle. Now what I can do is, this volume of this water will obviously be equal to the volume of this substance, right? So I can get a relation that this volume is actually of this displaced liquid and it is obviously equal to the volume of the substance. So this V written over here can be mentioned as the volume of the substance, right? So the buoyant force, now what I need to do is, I never need to consider this case, I never need to have a bucket full of water. What I can do is, I can just calculate the volume of it and just know the density of the fluid in which the block has been placed or the object has been placed. So rho is the density of the fluid, V is the volume of the object, and G is obviously acceleration due to gravity. So the buoyant force acting on this object will obviously be equivalent to rho Vg. Pretty clear? And this is the expression for buoyant force. So I need all of you to remember this expression, that whenever I talk about buoyancy or buoyant force, we need to calculate the buoyant force, and its expression will obviously be equal to rho, that is density of the liquid in which the object has been placed, into V, and V is what? Volume of the object when it is fully submerged. And if it is not fully submerged, suppose it's partially submerged, then the amount of volume which has been submerged. Okay, so suppose if I talk about this object and I say that only 4/5 portion of this object has been submerged inside water. So I need to take 4/5 times V only. I will not consider the entire volume again. Okay, so whatever volume of the object which is inside that liquid into G, and what you will get is you will get the expression for buoyant force. So I suppose you all must have understood and got the clear picture about what buoyant force is all about. Now let's move ahead and talk some very standard cases. Okay, so this is obviously loss in weight, and it is obviously equal to rho Vg, and we have just discussed it now. Now let's talk about the cases of flotation, sinking, and when the object is at rest inside a fluid. So suppose this is the first case, and the case over here is that objects float. So as I told you previously, you must have seen those plastic balls and even those Costco balls. When you throw it in water, a part of it is outside water and a part of it gets submerged. And what is the reason behind that? So the effective reason behind that is that the density, the effective density becomes lesser than rho, and this is about a substance which is entirely made of that material, but you obviously know that there is air inside that Costco ball, so it's not entirely made of rubber. If it is entirely made of rubber, then it will obviously sink, but the construction is made such that the effective density becomes lesser. Or for a better picture, let's consider this case, how we got this figure into action. How we got this figure? So let's just analyze. Suppose a body has been placed inside water. Now only two forces are acting on it. So one of the forces will be mg, right, and the other force will obviously be buoyant force, and this is of a significant amount, so we will have to consider it always. Okay, so what happens is whenever you are actually measuring things in air, so you never consider that loss in weight, because that loss in weight, the buoyant force in air is of very less amount. But whenever I talk about a fluid, and the fluid has a density in the range of 10 to the power 3 kg per meter cube, then I will definitely have to consider force due to buoyancy always. Okay, so two forces are acting, buoyant force and mg force, and the entire stuff, the entire thing, whether it will float over here, whether it will be at rest, or whether it will sink to the bottom of this bucket, will depend upon which of the forces is more. So suppose mg is greater than fb, then it will come down. If fg is equal to fb, then it will stay as it is, and if fb becomes greater than mg, then what fb will do, it will just make the object move upward till a point where fb decreases. And how fb can be decreased? Fb can be decreased when the amount of volume which is inside water decreases. So what happens is, suppose the object is kept over here, fb will increase and it will make the object move upward till that some amount of the object's volume is outside water, and in that case what happens is the effective volume inside water decreases, and as a result fb decreases. So fb decreases till a point it becomes equivalent to mg. Okay, I think you got a clear picture about what we will be studying about. So over here what happens is, we have kept the object inside it, fb was greater, and it made the object move upward till a point it got out of that water surface, and over here obviously fb has decreased because some amount, if you can see some amount, let's say suppose it's k fraction of the object is outside water. So what will be the fraction of the object inside water? I can write it to be 1 minus k. Yes, very clearly sir, you can write it to be 1 minus k, because the entire fraction has to be 1. So if I take k can be any fraction, 4/5, 1/2, 2/3. So suppose k fraction of water object is outside water and 1 minus k fraction is inside water. Okay, so the buoyant force acting on this object will obviously be because of this 1 minus k fraction. Okay, so this 1 minus k fraction will be actually playing a role in generating that buoyant force. So what will happen is, I have expressed it like this, that now suppose immersed volume is only Vi. Okay, so the buoyant force acting over here, this is the buoyant force. This is the buoyant force. So the buoyant force will be rho Vg, and what is mg? Mg is what? Mg is rho, that is, sorry, not rho, sigma, that is density of the object into its volume, entire volume obviously, because mass is because of the entire volume. So sigma into entire volume into g. So what will happen? Gg will get cancelled out, and what will remain up with, that Vi upon V, that is immersed volume upon V, will be equal to sigma upon rho. So this relation is very important. This relation is actually very important because what happens is sometimes the question is asked just giving you the density of the object, and they ask you how much amount of water or how much amount of object is actually inside water or outside it. So this relation can actually help you in determining what will be the amount of volume which is immersed and what will be the volume which is outside. So you can just do 1 minus Vi by V and you can actually find out the value of the body which is outside water. Okay, and if I talk about the same relation VO which is outside divided by V, it will be just 1 minus sigma by rho. It will be equal to rho minus sigma by rho. Okay, so I suppose you have understood this result of case of flotation. Now if I talk about case of rest, so what will be the case of rest? So in case of rest, what happens is that mg force is equal to that rho Vg force. Okay, buoyant force is rho Vg and it is equal to mg, and what I can deduce from here is I can write this mg to be sigma, that is density of the object, into V into g. This Vg will get cancelled, so sigma will turn out to be equivalent to rho, and this is the case over here. So if the density of this object is equal to the density of the fluid, then it will obviously remain at the position where it has been placed. And if I talk about the case of sink, so over here what happens is if sigma is greater than rho, that is the density of the object is greater than rho, then it sinks to the bottom, and at the bottom what happens is a normal reaction force begins to act where it got contact with the bottom of the beaker and bottom of the container, and this normal force in relation with the buoyant force will actually balance this mg force. So the normal force plus buoyant force will actually balance that weight, that is mg force. Okay, so this is the reaction force, this is the buoyant force, and this is your mg force, and so normal reaction can be calculated in such a fashion. This is obviously your mg minus rho Vg is your buoyant force. So I suppose you have understood the entire thing about cases of flotation. Now very simple and a very confusing question as well, but a very interesting one. So what the case over here is that they have stated that a piece of ice is floating in water. Okay, very well. What will happen to the level of water when all ice melts? And this is a very standard case. So if I ask you people, then first thing popping in your mind will be, okay, so we are in a world of global warming, and it's every day spoken that when Earth's temperature will rise by 1 or 1.5 degree, entire ice will melt and the level of the oceans will increase. So this gives a picture that I can just consider a case that suppose there's ice, and ice obviously floats on water, okay, because ice density is, the density of ice is 900 kg per meter cube, and if I talk about water, so water's density is 1000 kg per meter cube. So ice obviously floats on water. Ice floats on water because its density is lesser than water. Now I will get a picture that, okay, suppose and I'll just tell you, we just calculated, right, that Vi upon Vo, that is immersed volume upon total volume, is equal to 900 by 10. So this says that 9 by 10th of the entire ice will remain inside water and 1 by 10th portion will be outside water. Okay, so now I can get confused that, okay, so over here also when the entire ice melts, the volume should rise. But that's not the case. That's seriously not the case. That this entire ice, when it gets melt, the level of water remains unchanged. And why it is occurring, I'll just tell you how. Okay, so then how due to global warming the level of seas will rise, and I'll tell you that also. Okay, so just wait for a while. When I'll discuss these two cases, I'll be discussing this, and this is your homework, so you will be discussing, thinking about this and telling me in the chat what will be the answer. So now let's talk about the case where ice is kept and it gets melt, and because of that if the level of water is changing or not. So suppose I clearly told you people that 1 by 10th of the ice is outside water and 9 by 10th is inside water. Okay, so this is 1 by 10th and this is 9 by 10th. So now at this point, suppose the level is over here. The level is over here. So this 9 by 10th amount or volume or the fraction of ice which is inside water must have displaced some volume in the water, right? And what was the amount of that displaced fluid? So that amount can be very well calculated by, so I can write it to be displaced volume, and that will be equal to whatever volume is inside water, and what is its volume? So it will be 9 by 10th of the entire V. Yes, yes sir, pretty right. And I can replace this V by the mass of ice divided by the density of ice. Yes sir, you can definitely do that. So what is the density of ice? So the density of ice is obviously 9 by 10 times m upon density of ice will be 900 kg meter cube. Perfect, perfect. This gets cancelled by 9, and finally what I am remaining is with m by 1000. Okay, so the amount of displaced fluid is coming out to be m by 1000. Now this 1000 kg per meter cube, what it is? So kg per meter cube is obviously in the denominator. Okay, so 1000 kg per meter cube is how much? It is equal to density of water. So I can replace it by mass upon density of water, and mass upon density of water will be what? It will be actually equal to the volume which is being displaced by it is equivalent to the volume of this entire object. Are you getting my point, what I mean to say? So this V which you have calculated over here, mass upon the entire volume of this ice. Suppose now this entire volume of ice gets converted into water. This entire volume of ice gets converted into water. Then how much amount of volume will be released, or how much amount of volume will be displaced? How much more amount of volume will be added to this existing fluid? So we need to calculate its volume, right? So what will be its volume? Its volume will be total volume. Suppose this entire ice has got converted into water. Then the mass remains same. Mass cannot be changed. So the mass initially of ice will be equal to mass later on when it gets converted into water. So the volume will be total mass upon whatever its density. So now it has got converted into water. So now its density will be m upon 1000 kg per meter cube, right? M upon 1000 kg per meter cube. And as you can see, when it got converted into water, then also m upon 1000 kg per meter cube amount of volume is being displaced. And when it is presently in the form of ice and only 9 by 10th portion of it is only displacing volume inside water, then also the amount of displacement of water is the same. So what I actually mean to say is when it gets converted entirely into water, then also the amount of displaced fluid will be same as it is right now. So there won't occur a change in its length or whatever height the water level has maintained. And this was all about this expression. Okay, so now getting back to this global warming thing, so I can get that picture when I am discussing this and this. Okay, so now let's suppose what will happen if the beaker is filled not with water but with a liquid that is denser than water. Now let's take that case. Okay, so now let's take the case wherein again suppose this k fraction of water, is over here, and 1 minus k is obviously over here, right? Okay, so what will be the amount of displaced fluid? What will be the amount of displaced fluid right now? So the amount of displaced fluid right now will be what will be the value of k? Let's just determine the value of k. So the value of k will obviously be equal to whatever is the density of ice, that is rho of ice, divided by what is the density of liquid. Okay, so in that manner I can actually find the amount of k. I can express it in Vi by V, and Vi by V is what? It is the value of k. So okay, this is the value of, and right now we haven't considered the liquid to be water. So now in this case, when only k fraction of this ice is inside the liquid, then how much amount of volume is getting displaced? So I can find the value of displaced fluid, and the amount of displaced fluid will be equal to volume of this entire stuff. And what is the volume? It is k times total V, total volume V of ice. And how much is k? It is equal to rho of ice divided by rho of liquid, and I can very well replace the entire volume of this substance by its mass into rho of ice, right? So it gets cancelled, and what it is turning out to be? It is turning out to be m upon rho of liquid. Okay, so this is the displaced liquid right now. Now suppose this entire ice now melts. So now what volume of water will it displace? So the entire volume V which get converted into water, it will be the displaced amount of fluid over here. So let's just calculate that volume also. So what will be the value of that volume? So in that case, suppose this got converted into ice, this entire ice got converted into water. Now what will be the amount of volume which it will displace? It will be equal to I can find the value of V to be m upon whatever is the density of water. So what is the density of water? Density of water is rho W, and that is so what I mean to say is that when it gets converted into ice, this will be the volume displaced. Okay, this will be the volume displaced when it gets completely melted and it converted into water. This will be the amount of volume displacement, and depending upon that the level will rise. And in this case, when a k fraction of only is inside water, this is the amount of displaced water. So this is the displaced water when submerging or when ice and that liquid is there, and this is the amount of displaced liquid when it got converted into water. Now just tell me, if this is greater than this, if rho of liquid is greater than rho of water, then obviously displaced fluid over here will be lesser as compared to the displaced fluid over here, right? Are you getting my point? So depending upon, then I can that very well calculate what will happen when the liquid is denser than water and when it is lighter than water. Okay, so let me just erase this stuff and give you a clear picture about it. So this will be the displaced fluid before the melting has occurred. Okay, so when ice and that liquid is there, then the volume of displaced, the displaced volume will obviously be equal to m upon rho L. Okay, and when water, this entire ice got converted into water, then what is the entire scenario? What is the amount of displaced liquid? So in that case it will be m upon rho of water. Now you can very well find out what will happen when water is denser or lighter than that liquid. So suppose the liquid is denser than water. The displacement, what will be the effective change in the height of water when the liquid is denser than water? So this liquid is denser than this water. So obviously in that case, the displaced fluid over here will be lesser than the displaced fluid over here, right? So this is less than this when I talk about this case. So Vd will obviously be lesser than Vd dash. Vd will be obviously lesser than Vd dash, and in this case Vd will be greater than Vd dash. So now what occurs is when ice and liquid are present, in this case, then there will be a level maintained, and now as the ice gets melted into water, the displaced amount of liquid increases, as you can see over here, and since it increases, the level of water will also increase. Okay, so this is the case which is happening in case of global warming also, when because of the oceans are not of fresh water, they are of salty water, right? So their density is obviously greater than the density of fresh water. So when this entire ice melts, what will happen? Obviously the amount of displaced fluid will be greater than what it is being displaced right now. So as usual, the level of water will increase, and this is the danger which we are facing, which we are about to face in the coming decade or years. And due to this, so many island nations which are completely surrounded by water will have their coastline getting decreased by a great amount. Now if I talk about this, that the liquid is lighter than water, its density is lesser. So the case becomes this, that the displaced fluid when ice and water were there was more, and now when it has melted it is less. So the level will definitely decrease. Okay, so I think you got the entire idea or entire video, entire question what is occurring over here, and I suppose you have understood it. If you are facing any doubt, you can ask it right away, and if you love this expression, kindly like this video and share it with your friends. Maybe they are also in need of such explanation, and they will also get a clear picture how global warming can actually increase the level of water in oceans. Okay, now let's move ahead and talk about further topics, and the next topic is of steady flow or streamline flow. So what steady flow and streamline flow actually are, that you must have seen the flow of water. Obviously now we are moving ahead and we have just stopped fluids at rest, and now we are slowly moving towards fluid in motion. Okay, so and trust me, it's a very interesting topic. Okay, there are so many live examples which you can relate with just to understand and analyze this topic of fluids in motion. Okay, so now let's take this case of steady flow or streamline motion. Now what steady flow or streamline motion is? Obviously in a very layman term, I can say that if the flow is not very random, then obviously the flow is steady. Okay, and in a mathematical sense what it is, I'll tell you very nicely, but just look at this streamline. So what happens is, whenever a fluid is flowing, if the velocity or the path followed by all the particles, say suppose you have just fixed one molecule or one particle of that fluid, and it is moving, consist of, if it is moving along one of the streamlines, consider any one of the streamlines, suppose you are considering this streamline. So water molecule is just following this path, and the water molecule just before that is also following this path only, then this entire motion is said to be streamline. Okay, are you getting it? So this is what about streamline and steady flow. They are known by steady flow and streamline flow, and the opposite to this is obviously turbulent flow. Now let's look at the definitions. The fluid of flow is said to be steady if all the particles of the fluid passes through any given cross section with same velocity. Obviously the velocity should be same, or else randomness will occur. And what is turbulent flow then? So velocity of different particles passing through the same point may be different and change with time. So their velocities are different, their paths are different, they can just cross each other's path, and they will not follow what their predecessor has followed. So the successor is not following what their parents have told, so then a turbulence will occur, and this is what about turbulent flow is. So motion of water in a waterfall, obviously. And I should tell you that tap water even, so suppose, just do one thing, just do this exercise. You obviously will be having a tap at your home, right? So just open this nozzle, okay, just pull it up, and what happens is water will obviously come out of this opening. So for the initial path, for the initial few centimeters, the flow of liquid, you will find it to be very streamlined. It will be streamlined, but as soon as the velocity increases, and based on the velocity only, we can actually detect whether the motion of the particle will be turbulent or it will be steady. Okay, and there is a particular Reynolds number to detect it as well, so we will be discussing about that as well. But for just an example, just to give you a clear idea, just open your tap, and for the initial few centimeters, what you will observe is that the flow of liquid is actually very streamlined. It's coming in path, and the preceding water molecules are also following the same path. But after some time, as the velocity increases, the path becomes very random, and the water just moves like this. Okay, and this thing occurs because of turbulence. Okay, so there is turbulent flow at the bottom, and there is streamlined flow at the top as well. So you can just observe it and just analyze what I am telling you about, and let's mathematically analyze what streamline actually is and what streamline or steady flow is all about. So equation of continuity is very well in action whenever I talk about steady flow or streamline flow. Okay, and what is equation of continuity? It just says that the amount of water passing through a particular area per second will obviously be constant. Whatever be its area, it will remain constant. So suppose I am just imparting or moving 5 kg of water through a very big cross sectional area every second. So when it reaches a pipe of bigger size, then also 5 kg of water will only pass through that cross section per second. There is no element through which extra water can enter, right? Obviously the input is of 5 kg per second, so the output at every point should also be 5 kg per second, right, through a particular cross sectional area. And this is what equation of continuity is all about, and it has been derived using this concept and this understanding only. And finally what I want you all to understand is that this is equation of continuity. This is the mathematical expression that rho 1 A1 V1 will be equal to rho 2 A2 V2. Volumetric flow rate will always be constant. Okay. Now if water is of same density, then this rho 1 and rho 1 will get cancelled, and finally what you will remain with is a very beautiful equation known as equation of continuity, that is A1 V1 plus A1 V1 will be equal to A2 V2. And the best way to actually analyze what this equation is, that you can do one thing, you can just catch hold of a gardener, ask him that you will do the gardening today, and you will have a pipe. So you can obviously view him even that when he is about to water the plants, he just presses the end point of that pipe, and in doing so the amount of path, the length of the path increases, the projectile path increases. And the reason is that whenever he is increasing the area, then the velocity decreases, and whenever he is decreasing the area just by pressing that end point, the velocity increases. And as usual, if the velocity is increasing, then the path will be more, the horizontal range of that projectile motion will be more. So just consider this is mind, this is very important, and we will be using it very nicely slowly and just in a moment or so when I'll just discuss about Bernoulli's theorem. So in the application part of Bernoulli's principle, I'll be using this equation and defining what is velocity of a flux even. Okay. So this was all about equation of continuity. Now let's move towards the very beautiful and very interesting Bernoulli's theorem. So students face difficulty. They face actually difficulty while studying the applications of Bernoulli's theorem, and trust me, it's a very interesting concept that I can relate with so many things. That during if some people of you are from Odisha or that eastern coast of India, they surely have witnessed those thunderstorms and heavy winds with so great velocities. And what happens during those times is the roof of if the roof is not of a pakka house, if it's of a kacha house, then the roof just moves away, it just flies away, flies off the entire house. And the reason to that is Bernoulli's theorem. If one more example, if you have ever wondered why people have stopped you from standing very close to a moving train, a very fast moving train, and why it occurs, the reason to that is also Bernoulli's theorem. So why is that occurring? Now the airplane lift, the entire construct of an airplane, do you people even think that airplane, the simple airplanes which are actually carrying so many passengers on a daily basis, can they work on moon? No, they cannot, because they are working because of the presence of atmosphere. Okay, and the reason is Bernoulli's theorem. The swing of a cricket ball or the swing in a football game. So if you have ever seen a penalty kick or so many kicks, those free kicks, they never followed a straight line path, they always have a curved path, right? The reason to this is also Bernoulli's theorem. And there are so many examples to this, actually I cannot tell you. And all these examples, all these phenomena can very well be explained if you have a very good understanding about Bernoulli's theorem. And what it says is, there's a very simple expression to it. It just says that energy inside any moving fluid is always constant. Okay, this is a very simple statement, and it's all about energy conservation. So what it says is, whenever a fluid is moving, and obviously the flow should be steady, so we are not encountering any losses even, so energy of any moving fluid is constant. That's what it says. And based on this relation, what I can finally deduce is that energy in a moving fluid can be stored in three segments. So one of the segment will be because of its velocity, that is kinetic energy. The other segment will be because of the potential energy, because of the height at which water raises. And you all must have seen that you have an overhead tank, right? And all of you must be having an overhead tank, and if you have an underground tank, then you always have to run a motor if you want those fresh water, or you want water running through your pipes. Then why you have an overhead tank? The reason is that water has a potential energy stored in it. So the second segment is obviously water energy stored hoti in the form of potential energy, and the third segment is because of the pressure even energy gets stored, and because of the pressure water molecules come closer, they go far away. So energy gets stored in the form of pressure even. So there are three segments: pressure, potential energy and kinetic energy. And the summation of all these three energy remains constant, and this is what Bernoulli's theorem is all about. So a very simple statement, it just says that and obviously these relations are not having the dimensions of energy. They obviously have been modified to give a very easy expression to it. So the entire expression of this energy conservation has been converted in the form of equation, and this is not a very big thing to convert it, but all I want from you people is just remember this part, that P plus half rho V square plus rho GH will always be equal to constant. Okay, and this is what Bernoulli's theorem is all about, and so many things can be understood using this result only. Okay, so suppose I take a cross section of pipe, small element of pipe I have taken, and the cross section over here is having an area A1, the cross section over here is having an area A2, and obviously A1 is lesser than A2. So and they are at a height difference as well. So how Bernoulli's theorem can be applicable? It just says that suppose P1 is the pressure of water over here, P2 is the pressure of water over here. So P1 plus, suppose the velocity of water over here is V1, so half rho V1 square plus rho G H1, and obviously potential energy, you very well know, you can never ever define a potential energy, you can always define a potential energy with reference to something. So here is the reference, we have considered U to be equal to 0, Okay, we have considered the reference line for potential energy. So over here we can express it to be rho g h1, and h1 is the height over here. And similar kind of a thing we have done over here. So this energy over here will be equal to P2 plus half rho V2 square plus rho g h2, and this is what Bernoulli's theorem is all about. Okay, okay. Now let's move ahead and discuss some of the very important applications of Bernoulli's theorem. So the very first application of Bernoulli's theorem is venturimeter. And what happens is a fluid is made to run from this type of cross section. So different height of water develops over here, and I'll just tell you what is the difference of H1 minus H2 over here. So we can very well find out to be, suppose this is open to air, right? So over here the pressure is P naught, over here also the pressure is P naught, and I can very well calculate this pressure over here and this pressure over here, and they obviously are in motion. So the pressure over here and pressure over here, say suppose the pressure over here is P1 and the pressure over here is P2. So this entire segment of water is in motion, right? This entire segment of water is in motion, and the water over here are static. So over here those concepts which we have studied, that at P1 P2 point, at P2 point the pressure will be equal to P naught plus rho gh2, and at P1 point the pressure will be equal to P naught plus rho gh2. Okay, and between these 2 points I can just use the concepts of Bernoulli's principle, and doing that same thing I can very nicely find the value of H1 minus H2. Okay, so this experiment is used to know the velocity, the volumetric flow rate of any liquid. Okay, so using this method you can very well calculate the height difference, right? And in terms of that you can find the velocity of water, and how to do it I'll just tell you. So suppose over here P1 will be equal to P naught plus rho gh1, okay, and P2 will be equal to P naught plus rho gh2, okay, and between P1 and P2 I can use Bernoulli's principle, right? So what I can do is P1 plus half rho V1 square, and if you can see, then they both points are at the same height from the reference line if you choose anything. So if you're choosing a reference line like this, so they both are at same height. So the energy stored in the form of potential energy, you can write it on both the sides, but it will get cancelled. So there's no need to mention that element as well. So just the energies between pressure and kinetic energies because of the velocity. So P1 plus half rho V1 square will be equal to P2 plus half of rho V2 square. You can very well write down the value of P2, P1 over here, P naught will get cancelled, and H1, H2 you very well know, you can find the difference. So what you can find is, you can find the velocity V1 and V2. Now V1 and V2 there will be 2 variables in the equation. So for that also I have equation of continuity. So suppose area of cross section is given over here is A1, and the area of cross section over here is given as A2. So A1 V1 is equal to A2 V2, and replace any V1 or V2 using this result, you will finally get the result. So there is no gain in remembering those equations. Just remember the concepts, because they can be asked in any manner. They can ask you about the velocity, they can even ask you the value of H2. Okay, so remembering a formula will not suffice this result. You should entirely remember Bernoulli's theorem by that equation of continuity, and how to apply it. In that manner you can very well find out if the chips have been changed, if the concepts, the base have been altered, then also you will very well know how to solve this problem. Okay, okay. Now let's move ahead and talk about the next application of Bernoulli's theorem, that is velocity of efflux. Okay, that is velocity of efflux. So what this velocity of efflux is all about? So suppose you have a container, okay, and in the container a liquid has been filled whose height is h. Okay, the height is h of the amount of liquid filled in that container. Okay sir, perfect, perfect. Now I make a small orifice, I make a small hole at this point. I make a small hole at this point, and now because of this hole water will peep out of it. Okay, water will begin to come out of it, and it will not come out of it very slowly. It will eventually have a speed, and because of that the particle, the water molecules coming out of it will have a projectile path out of water. So this becomes a case of mechanics introduced, all those concepts of motion in 2 dimension applicable in the case of fluid mechanics. So this is a case of mixture of concepts, and JEE has always been loving those things wherein 2 or 3 concepts have been mixed up and so questions have been asked. So be very clear over here. So what happens is, because of this small orifice made over here, water water begins to move out of it, and the flow of water is pretty streamline in fashion. So, as you can see, streamlines occur, and all the molecules from a bigger area, they come and merge for a smaller area, and as obvious, the velocity of water coming down from this point will obviously be lesser than the velocity of water coming out from this small orifice, and we need to calculate this velocity. So, this velocity is expression you should very well remember, because it is asked directly and there is no difference which they can create over here. So, this velocity is always equal to root 2 gh, wherein this h is not the entire height, it is actually the height from the surface of the water between the orifice. So, surface and orifice, whatever is the distance, that is that small h. So, as this surface also decreases because of the water coming out, this velocity also decreases, right. So, this you obviously must have felt, and if you haven't felt, then do one thing, use any Pepsi, Coke bottle and fill it completely with water, okay. Fill it completely with water, using a small pin, just pierce it over here, okay. So, what you will see that initially the water was going till this level, then as the water level is increasing, okay, the projectile is also decreasing, the range of the projectile is decreasing because its velocity is decreasing, right. Its velocity is depending upon the height from the surface of the water till the point the orifice has been created, okay. So, this is the expression. Normally it will be under root of 2 gh when that orifice is very small as compared to the total area of this container. And suppose you have not made the hole using a pin, you use a big circle over here, big circular hole which is comparable to the total area of the surface, then in that case your area, the velocity will be of this expression, okay. If A is very less than capital A, then this expression turns out to be nearly equal to capital A square gets cancelled and the final result is under root of 2 gh. But if your small a is comparable to capital A, then what happens is the orifice, the velocity, if your small a is very less than capital A, then this value gets cancelled, and if it is comparable, then this is the result for velocity of an efflux, okay. So, try solving this question while I will be just needing some break, and you also take some break, drink water, and try solving this question while I will be back in a moment or so, okay. Bye bye. Okay, so I am back again and आप लोगों में से कितने लोगों ने आंसर सॉल्व किया है? Just tell me. Is it tough? You people haven't solved it yet. Okay, so now let's solve this question. What it says is that equal volumes of two immiscible liquids of densities rho and 2 rho are filled in vessel as shown in figure. Two small holes. So a hole has been made over here, a hole has been made over here. At a height h by 2 from the top and 3h by 2 from the top. Okay. They are from the surface of lighter liquid. If V1 and V2 are the velocities of a flux at these two holes, then V1 is to V2 is. We just need to calculate the ratio. So it's a pretty simple one, not a big thing. We have already discussed it. Okay. Now let's just solve it. Okay. So suppose P naught is the pressure over here, and this is obviously due to pressure. Pressure of atmosphere. Okay, so air molecules are continuously in air, they are exerting a pressure P naught at the surface of this fluid, and we can very well now calculate suppose the pressure over here is P1 and the pressure over here is P2. Okay, so over here it's a very simple thing. We have just seen the formula that this velocity V1 will be equal to under root of 2g into what is the height? It's h by 2. Okay, and this is the case when the density of the fluid is equal to rho. So it becomes very simple, and the case over here turns out to be that the velocity will be equivalent to under root of gh. Okay, perfect scene. Now if I talk about this point, okay, so what will be the velocity over here? So the entire liquid is not now same, so it is of rho, and the density of this fluid is 2 times rho. So then we will have to find out what will be the velocity. Just use Bernoulli's theorem between this point and this point. Okay. So suppose and obviously it will be in a streamlined flow. So the pressure over here will be, and P2, what will be the value of P2? So P2 plus half of rho into V2 square. Okay, and just imagine that the level of water is over here only. Okay. So P2, obviously it is also open to air, there is an orifice made, so P2's pressure will also be equivalent to P naught, and also P1 over here, it is also open to air, it will be equal to P naught only. Okay, so P1 and P2 both will have a value equivalent to P naught. So P naught plus half rho V2 square, this will be the value of energy stored at this point, is equal to the pressure, the velocity, and mgh over here. So what is the pressure? It is equivalent to P naught plus half what is the velocity? So rho times suppose the velocity over here is V dash. Okay, so V dash square plus rho into what is the height? So the height of water over here will be 2 times rho into h by 2, and the height of water over here will be rho g into h. So we need to take two components of water segments. The one component will be of this much height, so it will be equivalent to 2 times rho into g into this height, this much height. Okay, and this is because of this water level, so this will be equal to h by 2 plus this volume, this amount of water, this is rho into g into h. So this will be your entire expression. Now one more thing to understand over here is this area is very more as compared to this area, and since this area is very more as compared to this area, so the half rho v square over here will be very less. Okay, this velocity will be very less, and we can actually neglect this expression. So this expression will nearly be equal to 0. This P naught and P naught will get cancelled. So finally I can find the value of V2 square, and what it is turning out to be, so half of rho into V2 square will be equal to 2 gets cancelled, so rho gh plus rho gh, that is equal to 2 rho gh. Okay, 2 rho gh. And what is the value of V2 over here? So okay, one more thing here, as you can see, the liquid's density is not rho, it is 2 rho, so I have to mention 2 rho over here. So here also it will be 2, and this 2 will get cancelled by this 2, so over here only rho into V2 square will remain. I'm just again repeating myself. So here it will be P naught plus half of 2 rho, that is density of this liquid. Okay, density of this liquid 2 rho into V2 square. So this 2 and 2 gets cancelled, so over here only rho into V2 square will remain, rho will get cancelled, and V2, what I am getting the expression as, V2 will turn out to be, so under root of 2gh. Okay, so this is the expression. If you have any doubt, just rewind the video few seconds back and you will finally get that how V1 we have calculated. V1 can be calculated very easily, and for V2 we have just used Bernoulli's theorem again. So V2 can be very well understood using this fact of under root of 2gh. Now we just need to divide it up. So V1 is to V2 and V1 is to V2 is very simple. Root gh will get cancelled, so the final answer will be 1 upon root 2. Is that the option? Yes, C option. So let's see, we are correct. Yes, we are absolutely correct. We are absolutely correct. Khushi, good evening. So this will be the explanation for this question. Now let's move ahead and talk about surface tension. So what is surface tension? Any example, any application of surface tension? Yes, there is. So I have asked you a question in the previous crash course lectures that do you ever wonder why all the planetary bodies are nearly circular, spherical in shape? Why some random structures are not being created, like a cone is not created of any heavenly body, or a cube is not created? There is always a sphere. And the reason to this is that if I consider a V volume of any substance, so and if I construct a cone out of it, a cube out of it, a cuboid out of it, a hemisphere out of it, a frustum out of it, and a sphere out of it, so the sphere will have the minimum possible surface area. Okay, the sphere will be having the minimum surface area, and the minimum surface area means the minimum surface energy. Okay, so the reason to this is surface tension. The reason to that is surface tension. Okay, and I'll just give you a brief how that thing is getting derived. So more is the surface area, more is the surface energy, and things in nature are actually designed to move in such a direction where their energy, total energy count is getting decreased, and that's the region of stability. So everybody hunts for stability, even humans do, even objects do. So objects will also, if you just roll down a ball, if you will just roll down a ball from this point, it will definitely go down. And you have never asked this question, and you very well now know that this is because of the effect of gravity, mg force is acting. But if we talk in the sense of energy, so it will have a lesser energy as it moves downward. Okay, and this is obviously its more stable region. Okay, so everything wants to achieve the state of stability, and this is the reason the entire construct of planets and solar bodies, stars are near to spherical in shape. Okay, because sphere has the least surface energy. And if I now talk about surface tension, so let me give you a hint of what we will be discussing and what this is all about. So suppose we consider a water molecule, suppose this is a liquid and we consider a water molecule. So this water molecule, when it is inside water, it will obviously be attracted because of van der Waals forces from all the sides. Okay, from all the sides, whatever water molecules are there, they will be attracting it. Okay, so it will experience a force. It will experience a force. Now, if I want to just move this water molecule up to the surface, so what will happen? Now suppose this is a water molecule, so this entire sphere from all the sides, all the surfaces, all the ends, this water molecule is getting attracted. Now if I want to make it move to the surface of water or to the surface of liquid, then what will happen? The entire thing, the entire forces, because of the rest of the molecules, will only be restricted to this hemispherical zone. So now this water molecule will be getting attracted by only, this water molecule will be getting attracted because of this hemisphere only, all the water molecules which are created present in this hemispherical zone. Okay, right sir, perfectly. Now try and be very focused towards my statements. So earlier the state was that the water molecule was inside water and all the molecules were getting were just exerting a force on it, an attractive force. Now I want to move it in the upward direction, then obviously I will have to do some work, right? There are forces getting exerted on it from all the four sides, and then I want to make it move upward, so I will have to do some work, I will have to exert some force, right? That's pretty clear. And in that way only, the upper hemispherical, all the molecules on the upper hemisphere, they will just lose contact with that water molecule, and I have completely removed it and placed it on the surface. Okay, very well sir, very well. So yes, you have done some work, and now since I have done some work, that means my work must be stored somewhere, and yes, it gets stored in the form of surface energy. Okay, and now this water molecules doesn't want more surface energy, because more energy means more unstable. So they always want stability, so they will always try and resist them. So in doing so, you will always get a feel that a particular amount of force is being exerted whenever you are trying to create a new surface. Okay, there will be resistance from their end. The reason is, whenever you are trying to create a surface out of liquid, then the water molecules are getting separated from those attractive forces because of all the molecules surrounding it. You are creating a new surface and more water molecules are getting open to air. That means more amount of energy is getting stored in them. More energy means more instability, and they don't want that. So what they'll do, they'll just resist that, and in doing so, what you will feel that they are exerting a force on you, and that force is because of surface tension. Okay. So this is the entire explanation for surface tension, and it's a very common result. You might see so many examples. I have just given you an example as well. So now let's talk about the mathematics, how we actually express it. So surface tension is actually expressed as the force which they are exerting, the molecules are exerting, divided by the length, the whatever length of substance you are using. So F by L will actually give you the value of surface tension. Now if I talk in terms of surface energy, so surface energy is obviously also related with surface tension only. So surface energy is T times, that is surface tension, times surface area. Okay, so this is the explanation for surface tension using force and surface tension using surface energy. Okay, so do keep both these formulas in mind. Now if I talk about a liquid drop of radius r, so the liquid drop is made spherical in shape, right? And this is also a case to imagine why they are not made up in cubical fashion or conical fashion. They are always spherical. So because a sphere will have the least possible surface area, and obviously then in that case least surface energy will get stored in it, and obviously it will be more stable than any other structure. So the surface energy with or associated with a liquid drop is equal to T into 4 pi r square, and 4 pi r square is what? It is the surface area of that liquid drop made up of radius r, and T is the surface tension. Now if I talk about a soap bubble, so then soap bubble has two surfaces. If you have ever seen a soap bubble, so soap bubble has air outside also and even inside also. There is a very thin layer of soap which is actually creating that interface between in air. Okay, so the soap bubble is somewhat like this, and if I talk about a liquid drop, then liquid drop has water throughout it, but a soap bubble has water or soap infused with water only in this surface. So now the amount of surface open to air, or the interface of liquid air, is twice over inside as well and outside as well. So in it two surfaces are open, and hence the surface energy stored will be twice. So that's the reason behind this 2. So it will be T into 4 pi r square. Suppose a soap bubble is created of radius r, but it has two surfaces open to air, and more surfaces open to air means more energy. So the surface energy is actually twice. Okay, now I suppose you have got the basic idea behind surface tension. Now let's move ahead and talk about these important points as well. Now suppose there's a liquid drop which is broken down into so many n number of particles, so many n number of small liquid drops. So what will happen? Will you have to do some work in breaking this big drop into smaller drops, or can you be able to extract some energy out of it? So if you have to do some work, then this process will not be on its own. It will not move in forward direction, as in the case of chemistry. If you can remember the cases of chemistry, reversible, non-reversible reactions, or forward reactions, backward reactions. So if the energy is, if this process is an exothermic one, if energy is getting released, then obviously it will try and break down into smaller particles. But if it is an endothermic energy, that means if you have to do some work, then it will never happen on its own. So let's see what happens. So suppose we have a sphere, of radius r. So what will be its volume? Its volume will be 4 by 3 pi r cube, and it gets broken down into n small volumes. Okay, n small liquid drops. So the volume remains same. Okay, the volume remains same. So I can just express it to be n into 4 by 3 pi into small r cube, where small r I have considered the radius of these small drops. So from this I can actually very well create the relation between small r and capital R, and small r and capital R now you can very well understand that small r is coming out to be n to the power 1 by 3 times capital R. Okay, this is the value of small r. Now just see whether the surface area over here is more or the surface area over here is more. If the surface area of all these n small drops is more, then obviously you have increased the surface area, that means you have increased the surface energy, and this is not going to be an exothermic reaction. That means energy won't be extracted from it. You will have to provide them with an extra energy which will suffice the situation that more surface area will amount for more surface energy. Okay, so as you can see over here, if you just calculate it, then n times 4 pi r square will obviously be greater than 4 pi r square, which was the surface area of this initial liquid drop, the mother liquid drop. And since the total area of all these small drops is more, that means you will have to do some work, and the amount of work done will be equal to n into 4 pi r square. This is the change in area into surface tension. Okay, so I should be very well clear with you people that this will be the amount of work done, and you will have to do some work done if you want to break a bigger liquid drop into small n liquid drops. Okay, so this type of question or question based on this pattern, this concept, are used quite widely. They are asked so many times that what is the change, what is the work done, and this work done can be very easily calculated. You just have to multiply this surface tension with the change in surface area, and you can very well find out what the result is. Okay, two very important points are also there, and do keep them in mind as well. So surface tension, the value of surface tension decreases with increase in temperature. So as you move the temperature upward on an upward scale, the surface tension will decrease. Okay, and if I talk about adding some impurities in liquid, then also surface tension decreases, okay, by adding sparingly soluble impurities like detergent and increasing the adding soluble impurities like NaCl. So in both the cases the value of surface tension decreases. Okay, ठीक है sir, perfect, you have just made us understood. Now let's talk about an excess pressure, the concept of excess pressure. So what is the concept of excess pressure? So what happens is, whenever a liquid drop is created or a soap bubble is created or an air bubble is created in all those surfaces, or whenever a curvature is created, let's talk about curvature. So whenever a curvature is created of an interface, so I just cannot say that air is surrounding me, right? So many curvatures are being created between air and air. No, the curvature obviously should be of two different liquids, two different fluids. So there is a curvature wherein on the left hand side there is some other fluid, on the right hand side there is some other fluid. So a curvature has been created. So because of the presence of that curvature, on its concave sides pressure will always be more as compared to its convex side. So here is the convex side, that is inside pressure, we are terming it to be inside pressure, and outside it is the outside pressure, PO. So this inside, the concave one, wherein the concave side is lying, that pressure will always be greater as compared to the pressure on the convex side, and the rate, the change, the difference between them will be equal to 2T by R. What is T? T is obviously surface tension, and what is R? R is the radius of that curvature made. Okay, I should be very clear with you. The pressure on the concave side is always more than the pressure on the convex side, and the difference is 2 times T by R, where T is what? T is the value of surface tension, and R is what? R is the radius of that curvature. So this was the case about liquid drop. ये case किसका है? Liquid drop का. Now let's move ahead and talk about soap bubble. So as usual, I have told you people, soap bubble में दो surfaces होते हैं open to air. There are two surfaces. One is this one is that one. And on both the surfaces there is air, right? There is air, or any fluid where the soap bubble has been created. So since there are two surfaces, so we will have to take account two equations. So one equation will be over here. This is suppose inside pressure, so the inside pressure can be mentioned over here, Pi, and we have to consider a pressure between those layers of that soap. So that pressure can be termed as P dash. Okay, so now this P dash is on the concave side for this outer surface, okay, on the concave side, and PO is on the convex side. So I can create a relation like this, that P dash will be greater than PO and by an amount 2T by R. And similarly, this Pi is on the concave side and P dash is on the convex side if I consider the inner surface. So I can create an equation again, and this will be equal to Pi minus P dash will be equal to 2T by R. And on just adding both these equations, this P dash will get cancelled. So inside pressure will be greater than outside pressure by a quantity 4T by R. Okay, so this is a very important result, also keep this in mind. Let's move ahead and talk about an air bubble also. So what is an air bubble? Air bubble is obviously inside a liquid, inside a fluid. So this is the fluid and this air bubble, and there's obviously only air inside it, so it's only air. Okay, so there is only one surface. So do remember the terminologies, never confuse an air bubble with a soap bubble. Okay, both have a bubble, so there are chances of getting confused, but never ever get confused, because these silly mistakes can create havoc in your final result. So over here as well, Pi will be greater than Po, and as usual the difference will be equal to 2T by R, whereas R is the radius of curvature and T is obviously surface tension, the value of surface tension. Now suppose there are two bubbles coming close to each other and they are beginning to combining with each other, and they are not combining, a common interface has developed. So what will be the radius of that common interface? So there is a pretty good formula to remember it, just remember it. It will be 1 upon R is equal to 1 upon R2 minus 1 upon R1. R2 you can obviously see it is of the smaller bubble and R1 is obviously of the bigger bubble. Okay, and whatever is the pressure on the concave side will be more. So over here, as you can see, this is the concave side, so obviously P2 will be greater than P1, and as is written over here, P2 will be greater than P1, and P1, since P1 is on the concave side for this case, so P1 will obviously be greater than P0 also, and here also P2 will be greater than P0. So P1 will be greater than P1, P2 will be greater than P1, and that will be greater than P0 as well. Even P2 will be greater than P1 by a relation P2 minus P1 will be equal to 2T by R, whereas surface tension is of both these bubbles. If they are of a different liquid, then different liquids surface tension. So surface tension is different for set of different liquids. Okay, so whatever is the value of surface tension for these interface, you can just write it over here and the value will turn out to be like this. Okay, now let's solve this question, a very famous one, and I suppose many of you must have actually understood or solved it in a wrong manner. Okay, so two soap bubbles of different radii are connected to each other as shown. Choose the most appropriate alternative. So there are four alternatives given to us. We need to choose the most appropriate one. So we need to read all of them. First, the case is this. So what is given over here is there is a soap bubble created of radius R1. There is a soap bubble created of radius R2. Okay, fine. And now they are also interconnected using a very small straw or pipe. So now the options are: size of the bubbles remain unchanged, larger bubble burst instantly, and it can occur when sudden amount of pressure comes over here. Air flow from larger bubble into the smaller bubble, air flows from the smaller bubble into the larger bubble. So this thing of bursting, we cannot very specifically tell that to be, because we don't know what is the pressure at which the bubble will burst. So obviously on looking at the option, the B option is not suiting at all. Size of the bubbles remain unchanged, that can occur, and even these two can occur. So the maximum chances of answering the right one according to us is the C one, that air flows from larger bubble into a smaller bubble. And the reason is that we always tend to feel that heat flows from higher to lower, high temperature to low temperature. From a greater volume, always things flow from to the lesser volume. The cases of those liquids as well, how osmosis is also occurring. So we tend to answer this in this manner. But in case of air, you people also know air, how it flows, how wind flows everywhere. Just tell me how winds flow on earth even. You must be, many of you must be living near the coastal area. So how wind is flowing over there? Wind is flowing only because of pressure difference. So wind flows from a region of higher pressure to a region of lower pressure. So that's what the case with air as well. If the pressure in this R2 inside this larger bubble is more as compared to the pressure inside this smaller bubble, then obviously air will flow from the larger bubble to the smaller bubble. And if the alternate is occurring, that is pressure is more in R1 as compared to pressure in R2, then obviously the flow of air will be from smaller to larger one. Pretty simple. So we just need to calculate the pressure, what it is, and how to do that. So we have just studied that suppose the pressure over here is P2 and the pressure over here is P1. So they both are lying on the concave side, and outside there is a constant pressure PO, that is the atmospheric pressure. We can mention it to be PA or P0. Okay, anything. So P1 will obviously be greater than PO by a range 2T by R1. Okay, right. And similar case with P2 will also be greater than PA but by amount 2T by R2. Okay, fine. Now which amongst P1 and P2 is more? So From PA we have to go a value of 2T by R1 and over here by 2T by R2. So which one, 2T by R1 or 2T by R2, which one is greater? Obviously since R1 is lesser, that means this amount will be greater than this amount because R2 is lesser as compared to R1, right? That means P1 will be greater than P2, and since P1 is greater than P2, so it very well tells us that the airflow will be from the smaller one to the larger one, and this is our answer. Okay, so this is the explanation for this part, and I suppose you all must have understood. Now let's move ahead and solve this question of angle of contact. So what is angle of contact? And you all must have seen, if you just pour, earlier days there were mercury thermometers, and sometimes or the others I also used to play that mercury got broken and it got spilled on ground or on land, and it used to create a small bubble over there. And if I take the case of water, so if some amount of water got drop on that floor, it was very easily able to wet the surface. It just got spreaded over the entire surface. So why these phenomena are occurring? The reason behind them is angle of contact, and angle of contact is because of surface tension. So there are some surfaces, there are some liquids which have the potential to wet some surfaces and not to wet some surfaces. So mercury in this case, I had a marble flooring, so on marble mercury had the capacity to form a drop, okay, to form a drop, and in that case it was not able to wet the entire surface. It will obviously form small drops, and if I took water and place it over there, then it was very easily spreading on the entire surface. But water also forms a drop, so water droplets you must have seen on a rose petal or on this lotus as well. So on those surfaces water has the ability to form drops. So what is the reason behind this forming of drops or able to wet the surface? The reason is angle of contact. So this angle, this is the entire construct of a structure which can form a drop. So if it is able to form a drop, then you can very well see that the angle of contact is obtuse, right? This angle of contact is obviously obtuse, and this theta is obviously depending upon the surface tension, how their values are changing. Okay, and based on this we will be discussing about capillary rise and capillary fall as well. So over here the angle is obtuse since this material, this liquid has the ability not to wet the surface but to form a drop on a surface, and if this angle becomes acute, then what it will do, it will just wet the surface, the water will get spreaded all over, and this occurs when the contact angle is acute. So based on that you can very well find out, and this angle of contact is obviously depending upon the relative cohesive and adhesive forces. So what are cohesive and adhesive forces? So cohesive forces are the forces acting between same liquids. So same liquid molecules attracting force, all those van der Waals forces are known as cohesive forces, and adhesive forces are obviously when two different liquids or a liquid solid interface, they are exerting force on each other. So because of their construct, because of their forces in action, the contact angle will either be obtuse or acute, and depending upon whether they are acute, they will be able to wet the surface, and if they are obtuse, they will form a drop on it, as in the case of mercury and a surface. And they also depend on temperatures. Yes, temperature also plays a very key role in determining whatever be the contact angle. Okay, now let's talk about this very famous capillary rise. So what is capillary rise? Okay. So what is capillary rise basically? So what happens is, if I have a container, and I place a very small tube, a kind of a tube in it, and that very small kind of a tube is obviously known as a capillary. Okay. So if I place a small tube in it, what you will notice is that in some surfaces the water inside that tube will rise, and in some surfaces the water inside the tube will fall. And why is that occurring? I'll just tell you. So the reason to that is obviously surface tension. Okay, because of surface tension only, either capillary can fall and capillary can rise as well. But let's consider the case wherein the capillary has risen by a height h, and let's calculate this h in terms of what all parameters are given to us. Okay, so suppose this height which the capillary, the water inside the capillary has risen is h, and there's a meniscus created over here in this pattern. Okay, so it's concave from the upward side, convex from the downward side. So this meniscus, we can very well evaluate the result that we have just understood that on the concave side pressure will be more. So outside it is open to air, that means at pressure at point A will be equal to P naught, and inside it will be PB, and PB will obviously be lesser than PA, okay. So I can just write it to be that pressure at PB will be equal to P naught minus 2T by R, right. Pressure at PB will be equal to pressure at A minus 2T by R, since A is on the concave side and pressure at A is what? Pressure at A is what? It's open to air, so the pressure is P naught, that is atmospheric pressure. Very well, sir. Now if I talk about this point, PC, so obviously since this entire liquid in this column is static and pressure increases with depth, so pressure at C will obviously be more than the pressure at B. So PC will have a pressure more than pressure at B, and the amount by which it is more than B will be equal to rho GH. जो अमाउंट होगा इंक्रीमेंट का, इफ यू रिमेंबर हमने जब फ्लूइड्स एट रेस्ट डिस्कस किया था, सो डेप्थ पे जाने पे किसी पॉइंट पे जो प्रेशर होता था P2 विल वाज इक्वल टू P1 प्लस रो GH. सो यहाँ पे वही केस लगेगा, प्रेशर एट C विल बी इक्वल टू PB प्लस रो GH. So I can write it over here that PB will be equal to PC minus rho GH, or PC will be equal to P plus rho GH. So this PC is what? Now this PC is on a horizontal level with this surface, and over here it is open to air, so the pressure will be P naught, so PC replaces by P naught, and we get a result like this. So these two PB we can equate, right? We can equate, and this P naught and P naught will get cancelled, and finally what we will get is this 2T by R is equal to rho GH. Clear? Very clear, sir. हमने यहाँ से h की वैल्यू निकाल दी, so h will be equal to 2T by rho g r. Now what is this r? So this r is the radius of this meniscus created over here. We can very well replace it, this capital R, by the radius of this capillary. And how? You can see this triangle over there, this triangle. So in this triangle, this is what? This is the radius of the capillary, and this is what? The radius of the meniscus which is being created. And this angle is theta, because this angle is theta, that is the contact angle, okay. This is the contact angle. So capital R cos theta is equal to small r, so that capital R can be replaced by small r by cos theta, and here goes our final result that we know the value of surface tension, we know the value of rho even, g even, and small r, that is the radius of the capillary even, and cos theta can also be very well determined. We know the contact angle whatever liquid you have chosen, okay. So now what I am going to do is I am going to relate this h with theta, okay. So if theta is less than 90 degree, obviously cos theta will be positive, and cos theta will be positive, then h will be positive. That means capillary rise will occur. And if theta becomes obtuse, that is greater than 90 degree, and what was the case? The case was over here. Those surfaces which do not wet the surface, for them the contact angle is obtuse. So if the theta becomes obtuse, that is greater than 90 degree, then in that case cos theta will be negative, and according to that h will also be negative, and that will reciprocate to the case of capillary fall. So in some cases what you will observe is when you just place this capillary, so inside this capillary, in the case of fall, what happened? The liquid got risen up and it made this meniscus, and in such cases what will happen? The liquid will come down and it will make this kind of a meniscus, okay. So this is the case of capillary fall and capillary rise, and you just need to memorize this formula, just replace the theta and you will get the final result. So I suppose I was very clear with the explanation part that how capillary rise and fall are occurring. Now let's move ahead and yeah, so rise of liquids, this is a case over here. So rise of liquids in a capilla of insufficient length. So as you increase the radius, you can very well see on increasing the radius, the height got decreased. So more and more I increase the radius, and according to that the height is getting decreased. So HR is basically constant and mass of the liquid risen is proportional to R. So this is all about how if the capillary is not made of sufficient length, or if the capillary's radius is more, then obviously the capillary rise won't be in effect. So the radius has to be a very smaller one if you want to observe the height to be more, okay. Okay. Now let's move ahead and talk about Reynolds number, the very famous Reynolds number, which actually help us in determining whether the flow will be either streamline, laminar or turbulent, okay. And how this number is calculated? So it is calculated by this expression, that is rho Vd upon eta. And what is eta? It is viscosity, and that I will be just discussing in a moment or so. So based on this, using this calculation, you can find the number, and if this number turns out to be lesser than 2000, then our flow is what? It is streamline. It is streamline. So based on this number, our entire flow of liquid will depend whether it will be a streamline or a steady flow, or it will be a turbulent flow. And if this number becomes greater than 4000, it will be a turbulent flow, and between those 2000 and 4000 it will be the transition phase, or there will be some element of streamline as well, there will be some element of turbulent flow as well. So you cannot be very sure. So just for all the calculations, just try that your Reynolds number is lesser than 2000, and do remember this equation if you want to calculate Reynolds number. And now let's talk about viscosity. So what is viscosity? You all must have heard about air drag forces from the time you have studied motion in 1D or 2D, or specifically in laws of motion, that whenever an object is moving, it experiences an air drag force, and we need to counter, or we need to actually, whenever we are creating bodies in motion, we need to take that element of air drag also. Even the construct of high speed rails, even the construct of airplane are made in such a fashion that the effects due to air drag can be minimized. Okay, so that pointed nose actually is because to minimize the air drag, and that air drag is obviously because of viscosity. So viscosity is just like, in a layman term, it's the friction forces exerted by a fluid because of the motion of objects inside it. Okay, so the best fluid can be air, so the motion of all the objects in air can actually be decoded using the concepts of viscosity. Okay, to study it, let's just imagine a case wherein this is a fluid. Okay, this is a fluid, and just consider it to be a fluid like a river water. Okay, so a river is flowing, and in it a water is flowing, obviously a flowing river. So the flowing river has velocity differentiated from the top till the bottom. So what I mean by that is that the velocity of the topmost surface will be the maximum, and the velocity of the bottommost surface will be nearly equal to 0, since the water molecules are attached to ground and ground is in static condition. So that water molecules will not be able to move that rapidly when I talk about the topmost layers of any river. Okay, so a particular kind of filter or a particular kind of differentiation occurs in the velocity, and this velocity changes from this top point to this lowermost point. A profile is getting developed, and based on that we can say, suppose over here, as you can see, if I go a height dy, okay, for a difference in height of dy, the change in velocity occurs of dv. So dv upon dy, a particular figure comes into action, that as we are moving downward and downward, the change in velocity is occurring, and the velocity is obviously upper velocity minus lower velocity. The highest velocity will be the topmost surface, and the lowermost velocity will be at the bottom surface, and it is nearly equal to 0. If I have to mention the flow of water in a pipe, so in a pipe also such kind of a thing occurs, wherein the velocity in the bottommost, or not the bottommost, the middle element, the middle side of the water elements will have their maximum velocity. And if I talk about the velocity of the molecules which are near to the surface of pipe, the surrounding ones, on the circumference ones, they will have a very minimal velocity, and the maximum velocity will be at the center one, the central points. And the reason to that is only viscous forces, because all the layers of water, they actually exert a kind of a friction force. So suppose this layer wants to move in forward direction. Okay, so suppose if I talk about the the topmost layers, it wants to move in the forward direction. So it will exert a friction force in front direction to the bottom layer, but the bottom layer, instead, following the Newton's third law, will exert a force in backward direction. So it will oppose the upward velocity, and also its velocity will be lesser as compared to the topmost one. Okay, and depending upon that, a velocity profile has been created from the maximum to the least. Okay, and from this only I can determine the value of viscous forces exerted between layers, and that viscous force will be equal to eta A dV upon dy. Okay, so dV upon dy is what? It's the velocity profile which is being created, the change in the amount of velocity with the change in height. Okay, and eta is coefficient of viscosity, and area is what? The surface area of the layers which are in contact, which are exerting viscous forces between them. Okay, so if I talk about the SI unit, so it is Pascal second, and there's a very famous name given to it as well Poiseuille. Okay, so 1 Poiseuille is equal to 1 Newton second per meter square or Pascal second, and the dimensions you can very well calculate. Just replace the dimension of Pascal and second, you will find the dimensions of them as well. Now if I talk about the Poiseuille equation, so the Poiseuille equation is also very important, and keep this thing in mind. So this equation is very much in sync with the equation of conduction. Okay, so it's dV upon dt and it is equal to here. So what happens is, suppose in a water pipe, we have pressure P1 over here and we have pressure P2 over here. So the amount of flow, the amount of water which will flow will actually depend upon the pressure difference, that is P, and the rest is kind of resistance offered by the material. So in the resistance part you have this eta as well, you have this L as well, and you have this value of pi r to the power 4 as well. So it's just kind of heat conduction kind of a thing, you can just relate it with that, that water wants to flow over there. So more amount of water will flow when the pressure difference is more. So that amount, this Q, is directly proportional to the change in pressure, the difference in pressure, and obviously while flowing water you will face some resistance. So this entire quantity A theta L upon pi r to the power 4 is kind of a resistance to it, and the entire relation is somewhat like this. So do remember it, you don't have to memorize the derivation part of it, because questions are asked directly on it, that there is pressure difference of P1, P2, suppose two pipes are given and the pressure difference are same across both the pipes, and so depending upon the radius, one's radius is twice than the first one, so what will be the rate of flow? Okay, so do remember it, how this Q is varying with R and with L. So with R it has a change with R to the power 4, and when I compare it with L, so it will have a change inversely related with L. So this is how Poiseuille's equation come into action and talks about the rate of flow of water, and mostly you will be discussed and asked about Stokes law. So what is Stokes law and the element of terminal velocity in it? Okay, so what is terminal velocity? I'll just tell you. So what happens is, first let's just remember it, that Stokes law says that that if a body is placed in a liquid, or in a fluid, then it experiences a viscous force, and they are specifically talking about a spherical body only. So if a spherical body is placed in a fluid and it has a velocity v, so then the body will experience viscous forces because of the molecules of water which are present around it. Okay, and this is actually different from those buoyant force that will also come into action, and that mg also comes into action, but this force of viscosity is because of the drag and because of the water molecules not allowing this ball to move. So it will experience a viscous force, and the expression of it will be 6 pi eta r into v, where r is the radius, v is the velocity, whatever velocity is it. So suppose that object is in rest, so then viscous force will never come into action, but if it has a velocity v, then obviously this viscous force comes into action, and this is what Stokes law is all about. And pi is obviously pi 3.14, eta is coefficient of viscosity, and based on this terminal velocities concept has arisen. And what is terminal velocity? I'll just give you a picture. So what happens is, suppose you're throwing a ball in a very deep ocean, you go just above the point where Mariana Trench is located in Pacific Ocean, and you drop a ball, you drop an iron ball. So what you will feel, it will obviously drown, right? It will obviously drown. So it will have a force here mg, and it will have a buoyant force rho vg. And you will definitely say that since sir mg is greater than rho vg, then it will have an acceleration in downward direction. And obviously since the acceleration is downward direction, its velocity will continuously increase, right? That's the case. But you are not considering the case of Stokes law over here, which says that whenever a spherical body, that expression given over here was ideally for a spherical body, but that doesn't mean that a body of any other shape will not experience that force. They will also experience that force of viscosity, but the expression is not very certain and very defined. But if I talk about a spherical body, then it will experience a force, and the amount of force will be in upward direction. It will always oppose the velocity. You can see this negative sign. It just suggests that whatever is the direction of velocity, the viscous force will act opposite to it. So it will experience a viscous force in upward direction, and this viscous force is not a constant value. So as acceleration increases the velocity, the value of Fv also increases, and there occurs a velocity. So acceleration is increasing, the velocity increases, and so in sync Fv also increases. So velocity increases more, Fv increases more, and there occurs a point wherein this mg is balanced by this buoyant force and this increased value of viscous force, and this is the point wherein the body will experience no net external force and its velocity becomes constant, and that velocity is known as terminal velocity, or what is written over here, and the expression is 2r square g upon 9 eta sigma minus p. And you can very well find the result. You just have to equate what? You just have to equate mg with fb plus fv, 6 pi eta into r into v. Fb will be rho vg and mg. Just equate these values. What you will get, the velocity is 6 pi eta r into v. The v over here, the velocity over here will be equal to vt. So वहाँ से v2 की value आप निकाल लोगे, you'll get this result. You'll get this result. Okay. So this is the result for terminal velocity, and I think you got the ideation behind the concept of terminal velocity and how it comes into action. So people doing skydiving as well, they are left from the top of an air, from the such great heights with the help of an airplane, they also come to a value of terminal velocity. It's not like that mg will continuously increase their velocity. That mg increases their velocity, and obviously rho vg buoyant force is not that much in amount on us bodies, but that viscous force becomes huge. So after some time at our velocity, the velocity with which we are falling on ground becomes constant, and the reason to this is this viscous force. Okay. So this terminal velocity is very common, and now let's consider two cases that suppose a body of radius r released from rest. So the cases of suppose I am in a ship standing just above Mariana Trench. So it's near down to around there's around 10,000 meters, I guess, and it's more than that. Okay, the depth. So I'm just dropping a ball on the surface. So obviously it has an initial velocity 0, and because of that mg, which is greater than rho vg, it will have an acceleration in downward direction. So its velocity will increase, but along with the increase in velocity, the viscous force will also come into action and it will also increase. So it will decrease the rate, with which acceleration was changing or increasing its velocity. So now if you suppose in this much time I had a velocity change of this much value, okay, then after that in the same time duration I will have a velocity change by this much amount, and the reason to this is that the acceleration is also decreasing because of the presence of viscous force. And after some great amount of time, the time to reach actually the velocity of terminal, or the terminal velocity, is obviously infinite, because this curve will meet this line near to infinity only, but you reach a point where the velocity is very close to the terminal velocity, okay, and thereafter with a greater time also the change experienced in the terminal velocity is not much more, okay. So this is the curve when a body is released from rest. Now what happens if I throw a body? So now if I throw a body more than its terminal velocity, then what happens is, suppose I have thrown a body which is more than the terminal velocity. So now what will happen? The value of Fv and rho Vg, and this is obviously what? Buoyant force. So buoyant force and mg. So this buoyant force plus rho Vg are obviously now much more than mg, because your velocity of throwing is more than your terminal velocity. So this Fv plus Fb are actually more than mg, and in this case the acceleration is in upward direction. So what this acceleration will do? It will continuously decrease your velocity till the point it reaches that Fv plus Fb is equal to mg. So in this case, such kind of curve you will experience that initially your velocity was more, and finally because of the upward acceleration your velocity will decrease, and finally after an infinite amount of time your velocity will become equivalent to Vt, okay. So this was about terminal velocity. Now let's solve this question. And understand what this question says is. So a spherical ball of radius r dropped from a height is falling vertically in air with speed v. The air drag acting on the ball is proportional to, and obviously the proportionality have been mentioned in terms of v and r. So the air drag force, we cannot express the proportionality in terms of r only, okay, or in terms of v only. We need to add the element of v and r both, Okay, so first, if it is thrown in air, then the concept of buoyant force will not come into picture because the buoyant force value is very less. So the air drag, now what it says is that the spherical ball of radius r is dropped from height h, and after some time it has reached a speed v. So that means it has reached its terminal velocity, and when the object is moving with its terminal velocity, the mg force acting will obviously be equal to the viscous force plus the buoyant forces, which over here we can neglect because the buoyant force in air are very minimal, and the reason is the density of air, which is very minimal. Okay, so this Fv, this is the air drag force, and this is obviously equal to m into g, right? Now this m, we need to find this Fv only, and how it is proportional to. So nowhere in the RHS R and V are there. So we need to replace this m. G obviously we cannot replace, G is a constant value. We can write this m to be rho into 4 by 3 pi r cube, and here comes our r. So here comes our r. Now what more I can do is, if I remember the expression of terminal velocity, so if you can see, terminal velocity is directly proportional to r square. Terminal velocity is directly proportional to r square. So what I can do is, I can just keep 1 r over there, and in place of 1 r square I can place my terminal velocity also. So finally what I will get is that this air drag force is coming directly proportional to, consider this r cube as r into r square, and this r square can be replaced by Vt in some terms or the other. So this r square will get replaced by Vt, and this r is obviously over there, so it will come out to be directly proportional to r into our terminal velocity. And is this the answer? Yes, this is the answer. So now I suppose you have understood this question as well, and this will be the end of this lecture. I suppose you have understood all the concepts of motion in not motion, I'm sorry, the mechanical properties of solids and liquids, and we have constructed all the concepts, we have cleared all your doubts, everything, all the subtopics, topics, we have considered all of them and discussed over here. Kindly go through these lectures. If you face any doubt during the explanation part, rewind the video for a few times and then you will get a clear picture about them. But this is not all. Obviously you need to practice more and more questions based on that. And how to do it? So in the description you can find the link to Extramarks the learning app. You can download it right away, and what it offers to you is you can get access to unlimited amount of questions on whichever topic you like, and whichever subject, whichever subtopic, what level you want, you can practice questions. Even you can give tests, and the results you can analyze. So those results are very nicely framed, which can give you a very good analysis report that which question took you more time, or which type of questions you are facing difficulty with, or which concepts you are not aware of. And based on that analysis report, you can obviously see these lectures which are daily live at 5 p.m. and obviously you can also refer these lectures to your friends, so they must be in need of it. And this will be all from my side. So we'll be meeting in the next session, and that will be, remember this date, it will be on 1st of Feb, the 1st of the next month 2022, and 5 p.m. okay, we'll meet in the next lecture. Till then, bye bye, happy learning, stay safe.